talk about Coulomb's law. This is a mathematical principle behind what we've been discussing for electrostatics. And Coulomb's law has a lot of really practical applications. First of all, let's go back to our gravitational force. Remember, F due to gravity, due to mass, is some gravitational constant g times the product of the masses divided by the distance between the two masses squared. Okay, you remember we did this, m1, m2, and r is the distance between them. Well, the electrostatic, or the electrical force, or Coulomb's law, is F electrical is K Q1 Q2 over D squared, where this is charge 1, charge 2, and D is the distance between them. Now I'll use D, I'll use R. It's the same thing. It's the distance between the two charges. And in this class, we're not going to worry about the size of the charges. We're going to assume they're infinitesimally small. Now, let's analyze Coulomb's law. Q1, Q2, and D, where D is the distance between. Fe is your electrostatic force. And so a lot of times we'll just call it our force. We always measure forces in newtons. Q1 is the charge of the first particle, usually the one on the left or whatever. It doesn't matter how you number them. Q2 is the second particle, and D is, of course, the distance between. Make sure your distances are in meters, and we will always measure our charges in coulombs. Now let's talk about Coulomb's constant. Coulomb's constant K is equal to 9 times 10 to the 9 Newton meter squared per Coulomb squared. Memorize it. You can think of it, if you get lost, as 9E9. 9E9. If you put this in your calculator, this means 9 times 10 to the 9. Just a shortcut. Now, F is directly related to the charges because it's right across the equal sign. So if I were to double Q1, I would double my force. If I were to double Q1 and Q2, well, 2 times 2 is 4. So I would quadruple my force. However, F is inversely proportional to D squared because it's 1 over D squared. So the same analysis we did with gravitational force will apply to electrical force. Now, if I were to double my distance, what would that do to my force? It would actually reduce my force by a fourth. All right, because it's 1 over 2D squared, and that 2 gets squared. So it's very interesting. The further you get away from a charge, all right, if this is my charge Q, the further you get away, the force goes down very dramatically, which is why the whole universe isn't stuck in a big pile, actually. Now, actually I already did these. If Q1 is doubled, what happens? Just kind of write a little 2 right there, and I see that my force is twice my original force. If D is tripled, okay, what happens when I put this in the denominator? I get 1 over 3 squared, or 1 over 9, so my force becomes 1/9, my original force. Now this one's fun. What if Q1 is tripled and D is doubled? All right, I'm going to erase this up here so we can write this. I like actually writing it on the equation. It helps me out, and I'm going to do it in another color. Q1 is tripled, so I'm going to put a 3 right there in front of Q1, and D is doubled. So this is 2, but I've got to square it. So I wind up with 3 divided by 2 squared is 3 divided by 4. So my new force is 3/4 my old force. You're going to need to be able to do this sort of analysis. Now, here's, the charge on an electron is negative 1.6 times 10 to the negative 19 coulombs. And the charge on a proton is 1.6 times 10 to the negative 19 coulombs. These are givens, all right? So if I say electron, you know the charge is negative 1.6. That negative sign just means it's an electron and negatively charged, while a proton is positive. Electrons and protons have the same charge, they're just different signs. Now, what happens to the total charge when they touch? Think about it. All right, let's say Q1 is 1 Coulomb. And let's say Q2 is, oh, I don't know. Let's make this 3 coulombs. All right, now I'm going to make them touch. As soon as they touch, the charge distributes evenly. So the total charge becomes the sum of the two. So the total charge of the whole thing is 1 plus 3, or 4 coulombs. So the total charge is 4. So what happens if I were to separate them? Think about it. The charge is evenly distributed. If I separate them, this one will be 2 coulombs, and this one will be 2 coulombs. Kind of cool. Let's try one of these where one is positive and one is negative. Say Q1 is negative 3 coulombs. And negative 3 coulombs. Let's try that again. Here in trouble here. Negative 3 coulombs. And let's say Q2 is what? Well, pin's not wanting to work. Goodness. Let's say Q2 is positive 3 coulombs. What happens when I let them touch? You're exactly right. You add negative 3 to positive 3, and what do you get? You get 0 coulombs. So this thing becomes neutral. Well, pen is acting up. All right. Now, let's compare gravitational force and electrical force. They're both inverse square. So that means it's 1 over r squared relationship. So the further you get away, the more the force decreases quickly. Gravitational force is a very weak force, while electrical force is a very strong force. It's not the strong force, but it is a strong force. Gravitational forces are only attractive. You can't have repulsive masses. While electrical forces can be attractive or repulsive. It depends upon whether you're dealing with two positives or two negatives, or a positive and a negative. Now we're going to talk about equilibrium. Equilibrium, you remember, is just when your net force is 0. Now, forces are vectors. So the net force is going to occur when the force from one particle is equal and opposite to the other particle. So let's just do a little quick diagram here. We'll do some problems later, but let's see. Suppose I have Q1. Well, don't know why it's not responding. Q1, Q1, and Q2. All right, sometimes you get to the edge of the pad and it's kind of messy. Now suppose they're attractive. So one is positive and one is negative. So the forces are attractive. There's going to be a point here where the force of 1 on 2 is equal and opposite to the force of 2 on 1. Now please don't let this scare you. Is that true? No, that's not true. Ignore everything I just said. That's rubbish. Happens, folks. It really does. Suppose I have Q1 and Q2. All right. Now, suppose they're both positive. All right. There's going to be a point in here where the force of a test charge, we're going to call that Q3, the force on the test charge is equal and opposite to the force from Q2. So the force of 1 on 3 is going to equal the force of 2 on 3. So say this test charge is positive. Let's look at the direction of these forces. All right, Q1 and Q3, I'm going to put my pencil on Q3. Now what is happening? What is Q1 doing to Q3? Because they're both positive, it's going to push it away. So this is the force of 1 on 3. Now I'm going to switch colors. What happens to the force of 2 on 3? Well, I'm going to put my pencil here because this is what it is acting on. 2 and 3 are both positive, so 2 is going to push 3 away. So this is the force of 2 on 3. So we see there will be some point, x, we're going to call it x, where the force of 1 on 3 is equal and opposite to the force of 2 on 3, where they're equal. Now say Q1 and Q2 are some distance d apart. I want to show you a cool little trick. What is the force of 1 on 3? Well, it's K, Q1, Q3, divided by the distance between 1 and 3 squared. So that's going to be divided by x squared. This has to equal F23. The F23 is K, Q2, Q3, divided by, now what is the distance between 2 and 3? It's d minus x. D minus x squared. Now look at what is about to cancel. All right, my k's are going to cancel. Q3 is going to cancel. So I'm left with this right here. Let me switch colors here. I'm going to go black. Q1 divided by x squared is equal to Q2 divided by d minus x squared, the whole thing squared. So you wind up with this quadratic that you can solve to find where charges are at, where would be the equilibrium of an electric force on a charged particle.